Okay, now picking up where we left off at. It says when a number written in scientific notation has a positive exponent on 10, what can we say for sure about the number? Now, what we can say for sure about the number is the number is equal to or larger than 10. It's equal to or larger than 10. Okay, now, if a number between 0 and 1 is written in scientific notation, what can we say about the exponent of 10? Now, first of all, we have to determine what type of numbers are between 0 and 1. We know those numbers would be decimals, because we want a number that's larger than 0 but less than 1, so those are decimals. Now, if we start off with a decimal and we change that to scientific notation, that means that decimal will begin with 0 point something. It could be 0.15. It could be 0.9999. It could be 0.543. But we know that those decimals fall in between 0 and 1. And in order to write this as scientific notation, we would need a negative exponent on the 10. Now, for number 12, it says fill in the blanks. If a number in scientific notation has a negative exponent on 10, to convert to decimal form, move the decimal place left, as we did in the previous problem, because the number is less than 1. Now, if you want to see this, you could go back to the previous video and look at problem number 9. So you can see this in action. All right, now we flip over to the back. Mainly I want you to look at problem number 13. It says write the result of the calculation on the calculator screen in scientific and decimal notation. Now, what we're really concerned with is the answer here. Now, if you have a TI calculator, whenever you have very large or very small numbers, it would end up giving you an answer that has an E in it. Sometimes it'll have behind the E a positive number or a negative number. So this is what this actually means. 7.44 E3 means 7.44. E would be the times 10. The number behind the E is the exponent. So E is the times 10. Just to illustrate that. So it says write the result of the calculation on the calculator screen in scientific and decimal notation. So to write this in scientific notation, it would be 7.44 times 10 to the third power, which we have. Now for decimal notation, let me circle that to indicate that that's your answer. Now for decimal notation, we'll take 7.44, and we see this 3 is positive. So we will go to the right 3, 1, 2, 3, and that will give us 7,440, and that is our decimal notation. Now we need to move on to page 87, and I believe that this is our last page for this exercise. Now we have a typical MP3 file fills about 4 times 10 to the 6 bytes of disk space. How many average songs can my iPod Classic, which has 80 gigabytes of disk space, hold? Each gigabyte is 1 times 10 to the 9th bytes. So what we have to do is do a conversion process. If you notice, everything else is in bytes here. So we have to take the 80 gigabytes that we had available from the iPod and change that to bytes. So we would take 80 gigabytes and multiply that. Now it tells us each gigabyte, which means 1 gigabyte, is 1 times 10 to the 9th bytes. So since gigabytes is in the numerator, we would know gigabytes will have to be in the denominator, and the numerator would be 1 times 10 to the 9th bytes. Now, Gigabyte and gigabyte will simplify out. And that will leave us, if we put this over 1, that will leave us 80 times 10 to the 9th bytes. Now we don't need to put it over 1 because we know anything divided by 1 is itself. Now here's the problem. This is no longer in scientific notation. So we need to make this in scientific notation. So in order to do that, we know it's a decimal behind the 80, and we have to move 1 place to the left. When we move that 1 place to the left, we have to add 1 to this exponent. So this would be 8 times 10 to the 10th power bytes. Now, we want to know how many songs would fit on this iPod. And we know the iPod took MP3 files. So we would take our 80 gigabytes that was converted to bytes, which is 8 times 10 to the 10th power bytes. And we would divide this by the 4 times 10 to the 6 bytes, which is how much a typical MP3 file fills. Now bytes will simplify each other out. Now what we could do, we could separate this here. We'll take 8 over 4 times 10 to the 10th over 10 to the 6th. And we know this is all bytes. Well, no, the bytes were canceled out. Okay, so now 8 divided by 4 is 2 times. Whenever you have the same base, you write the base, which is 10, and you subtract the exponents. 10 minus 6 is 4. So it'd be 2 times 10 to the 4th. And if you put that, if we make this into decimal notation, which we should, we have to move the decimal 4 places to the right, which would be 20,000 songs. That's how much the iPod could hold. Okay, now we move on to problem 15. It says use Newton's law of universal gravitation to feel the gravitational force between the Earth and Sun. The gravitational constant G is 6.674 times 10 to the negative 11. The distance from the Earth to the Sun is 1.496 times 10 to the 11th meters. The mass of the Earth is 5.974 times 10 to the 24th kilograms. The mass of the Sun is 1.989 times 10 to the 30th kilograms. The units of force are the kilograms meter per second square, also known as the Newton. So we would take the formula of force. Force is equal to G times m sub 1 times m sub 2 all over r squared. So F is equal to, we're given what G is, which is 6.674 times 10 to the negative 11th power, times. Now m sub 1 is actually, let me see, the Earth's mass, which is 5.974 times 10 to the 24th, times the Sun's mass, which is 1.989 times 10 to the 30th. And that's all divided by the distance. The distance here is 1.496 times 10 to the 11th. Now, when we put all this in our calculator, our final answer would be 3.543 times 10 to the 22nd, and the units would be newtons. So this right here would be our final answer. And I ran out of space, so newtons should go right behind this. Okay, now we come here to problem 16. It says Newton's second law of motion is F equals m times a, where F is force, m is mass, and a is acceleration. For a situation where the force is caused by gravity, say when you drop a bowling ball off of a building, we can use the universal law of gravitation with a is equal to G times m sub 1 divided by r squared. Legal disclaimer, if you drop a bowling ball off of a building, you're a jerk. Yes, funny sense of humor. Use the value of G, the mass of the Earth, and the radius of the Earth, which is 6.3781 times 10 to the 6 meters, to find the acceleration due to gravity near the Earth's surface. How does your answer compare to the value used in a typical physics course? A is equal to 9.8. For the record, the units for A for meters per second, or meters per second squared, if you like. Okay, so we would take this formula. A is equal to G times m sub 1 over r squared. A is equal to, our G was given to us in a previous problem, which is the 6.674 times 10 to the negative 11. But they said that was constant. Now, we will multiply this by m sub 1, which is 5.974 times 10 to the 24th power, which we got in the previous problem too for the Earth's mass. And we would divide that by the 6.3781 times 10 to the 6th power. Now when we put this, and we have to square that as well. When we put this in our calculator, it will give us approximately 9.801. And this is very close to our usual value of 9.8. And we are done.